All right, excuse me. Welcome back to the chemical reactions series of PowerPoint presentations in Mr. Voigt's science class. Our final presentation for the unit is on energy and chemical reactions. And in order to really do justice to this concept, we're going to have to think back to first try when we discussed endothermic and exothermic. So again, do you remember what exothermic and endothermic mean? Exothermic means the heat is given off, and endothermic means the heat is absorbed. In an endothermic process, the beaker would feel cool. In an exothermic process, the beaker would feel hot. Now, reactant molecules in a chemical reaction need to break bonds. Now, it takes energy to break bonds, so you have to put in some energy to break the bonds between the reactant molecules. But the product molecules form bonds, and when they form bonds, they release energy. So the overall quality of the reaction, whether it's exothermic or endothermic, depends on the amount of energy it costs to break the bonds, related to how much energy is released coming from making the bonds. Again, the amount of energy it costs and produces determines the net result. And if it's an exothermic process, that means that it releases energy overall. And if it's an endothermic process, that means it absorbs energy overall. To make this, maybe more concrete, essentially when you take energy to break bonds and you release energy to form bonds, it'll be endothermic if more energy is needed to break the bonds than you get from forming bonds. And if you get more energy from the forming bonds than it takes to break the bonds, then it's exothermic. Now, it's a little bit more complicated than what I've just described, because activation energy is the amount of energy required to start the reaction. Now, we know that wood can sit in a pile for many, many years and not burn, even though that wood is capable of burning. The wood is not going to burn until we give it enough energy at the start to start the reaction. Now, if we look at these energy diagrams, the energy diagram on the left shows an exothermic reaction, and the energy diagram on the right shows an endothermic reaction. Now, here we can see that the reactant particles are on the left, and the products are on the right. And the same is true with the endothermic graph. Reactants on the left, products on the right. You can see that the x-axis or is labeled reaction progress. So the further we get along the x-axis, the more products we're making, and the less reactants we have left. Now, the y-axis is labeled energy. So obviously, reactants have more energy than the products do in an exothermic reaction. This little speed bump on the graph represents the activation energy. Activation energy is the energy difference between the reactants and the top of the hill. You can see that in an endothermic process, the activation energy is significantly greater because the energy of the reactants is so much lower. Now, the energy that is given off in an exothermic reaction is the difference between the energy of the reactants and the energy of the products. The energy absorbed in an endothermic reaction is the difference between the energy of the products and the energy of the reactants as well. Now, overall, if the reaction goes downhill from reactants to products on an energy diagram, then it's exothermic. If the energy diagram is uphill from reactants to products, then it's an endothermic process. Now, reaction rate refers to how fast the reaction is going to occur. Now, we know if we throw a phone book into a fire, it's going to take a very long time for that phone book to completely be consumed with fire. However, if we take individual pages out of that phone book and throw them into a fire, it's going to be consumed quite rapidly. So the speed of the reaction is determined by how frequently the reactant particles collide. So if we can do anything to make these reaction particles or the reactant particles collide faster, then we will speed up the reaction. So how do we make a reaction go faster? We can do a couple of different things. We can stir it, first of all, and if we stir things in a liquid form, then it's going to make the reaction particles collide more often. we can increase the temperature. And what I mean by that is I really mean we can add energy, because if we add energy, the particles speed up. And if the particles speed up, then they're going to collide more often. We can also increase the surface area, which is what the phone book example is. Wood chips will burn faster than a log of wood because there's more area to be exposed to other reactant particles. And the last one is we can use a catalyst. Now, a catalyst is a specific substance, like a protein in your body, for example, that participates in the reaction as a facilitator. A protein in your body, for example, will grab one molecule in the reaction and grab a different molecule in the reaction, and it will slam them together in just the right conformation and speed so that that reaction can actually take place. But once the reaction has taken place, the catalyst then lets go and it goes back to normal. The important thing to remember is that a catalyst speeds up a reaction, but it does not actually participate or get consumed in the reaction. So the total amount of catalyst that you had at the beginning is the same as the catalyst that you have at the end. The catalyst does not change. It simply allows the reaction to take place faster. Now, we can make a reaction go slower in a number of different ways. We can stop stirring it. We can cool it down so the particles slow down. We can decrease the surface area. And the opposite of using a catalyst, the opposite of a catalyst is an inhibitor. Inhibitors are things that prevent a reaction from happening. We talked about proteins as catalysts. Proteins grab a reactant molecule and they grab another reactant molecule and slam them together. An inhibitor will actually grab a reactant molecule and then not let go. Examples of inhibitors are preservatives in food, things that prevent your food from spoiling. They prevent a reaction from taking place. So those things are inhibitors. Now, in class, we are going to watch a video on reaction rates, which just kind of shows demonstrations for how we can speed up a chemical reaction and how we can tell if these reactions are endothermic versus exothermic. And we're going to get a lot more practice at this too as we, in the next couple of days, witness some real chemical reactions in the lab and take observations of those things.